I want to explain you about the structure and evolution of stars. Let me share my screen. Yes. Here you see the visual binaries. We can see that we have different kinds of binaries, visual binaries, astrometric binaries, spectroscopic binaries, and eclipsing binaries. For visual binaries, we have physical and non-physical binary system. Here you see the physical binary system. Two stars are here and they have some contact in their orbits. And you see here a mass of a binary system is here, and in star A, maybe this star have a planet that orbit around it, and maybe this star also have a planet orbit about it, and maybe there is a planet which its orbit is out of these two stars' orbits, which will be more complicated. Here is you see the Alpha Centauri B, Alpha Centauri A. Separation is 14 seconds, and you see here the visual binaries. Astrometric binaries, there are two stars wobbling each other. As you see, Sirius A and Sirius B, that they wobbling each other. Also, we have eclipsing binaries that it depends on which angle we look at them. These binaries were born at the same time, so we can calibrate isochrone. And we have spectroscopic binaries. For spectroscopic binaries in SB1 or spectroscopic binary 1 system, we can just see the spectral line of one companion, because one of them is faint. In SB2 system, we see spectra of both stars. They have a shift from the spectral line, so one line is in blue and the other is in red line. As you see here, SB1, we have one line, but in SB2, we have two lines in blue and red regions. And sometimes they have overlap, as you see here. Also, again, we have BA. Here it is A plus B. Here we have AB, and here BA. That they move and change their location. But in SB1, again, we have just one line. And here you see the shift. It shifts here, the other shift here. And you see the shift of them. Sometimes they have overlap. And just for example, we have just H alpha line. From spectrum, we can, these are the spectrum of the Doppler shift in a spectroscopic SP2 binary system. These are spectrum of them. From the spectrum, we can have temperature, mass, luminosity, abundance of both companion. If the ratio of flux is not too much, we can see the spectra of both companion. Close and wide binaries. Close binaries are two companions are in the Roche lobe L1. As you see here, we have M1 and M2, and we have L1 Lagrangian 1, that they are in the Roche lobe or L1. But for wide binaries, we can say that two companions are out of Roche lobe and they are not near each other. If the satellites are in the Lagrangian points, for example, Lagrangian 1 or Lagrangian 2, or 3, or 5, or 4, they are stable. But if they are not in Lagrangian points, they are not stable. And in Lagrangian point L1, if one star will be more massive and more wider, it transfer its mass from this one, for example, M1 to the other one, for example, M2, from Lagrangian point L1, because they are near each other, and when it goes to the Roche lobe here, it transfers its mass from L1, Lagrangian point 1, to the other companion. But if they are not near each other and not in the L1 Lagrangian point, and they are far from each other, they won't transfer their mass, as you see again here. How binaries form? There are 3 ways: disk instability, core fragmentation, and N-body. During the main sequence and infusion, stars become lighter, and here you see in disk instability, primary component forms in overdensity and grow. It's one giant molecular cloud, and one star formed or was born, and then accretion burst instabilize says that disk and secondary companion forms. As you see, they have some density in a region, and then second companion will form. And both stars grow and migrate inward. They have a lot of gravitation to each other, and they capture each other, as you see here. So they will be binaries. Then we have core fragmentation. And here molecular cloud has angular momentum, and it has fragmentations, and 2 stars will be formed. It is the most probable scenario. They formed independently, and magnetic field is important. As you see here, we have one molecular cloud, but there are 2 independent protostars in the molecular cloud, in the same molecular cloud, so they are in the same age, and then approach and interact the gravitation and capture each other, and then both stars are grow and migrate inward. They capture each other, and they will be binaries. And we have N-body. For example, 2 or more, 3 or 4 stars will be close to each other and attract each other, and gravitation will be strong. Then they capture each other and then form a binary system. As you see here, we have 3 or 4 stars, for example, there, and they pass their path, and they cross each other. They go in their way, but suddenly they see each other, and chaotic motion, ejection, eccentric, binary, triple left. You see, they capture each other from their gravitation, and they will be 2 binaries, and then the other pass away its way. And difference between core fragmentation and N-body is in N-body stars probably do not have the same time, and they won't have the same age, so they won't fit in the same isochron. But in core fragmentation, they are in the same time or in the same age, and they will be in the same isochron. line, and they are all in galactic disk, not in star clusters. And here you see the binaries. For example, as I told you, they have we have two binaries, and then one of them goes to Roche loop. It becomes wider and bigger, and then it transfers its mass to the other companion, and then it explodes, and you see the explosion. And then companion merge again, red or supergiant with neutron star or black hole core, and also Wolf-Rayet star with compact companion surrounded by expanding envelope. And then again, we have secondary explodes as type 1b supernova, and then again binary relativistic star. Here we have supernova explosion, disrupt the system, two single neutron stars or black hole. And at last, we have merger of components with a burst of emission of gravitational waves. Here you see closed binaries. We have two stars from main sequence, and then one of them will be giant or supergiant, and the other again is main sequence. And then common envelope, they transfer mass, and one of them transfer mass, and they will be more larger. And then outflow of common envelope, and then white dwarf and main sequence star. And then giant or supergiant plus white dwarf. Here we have the super soft X-ray source, supernova type 1A. Here we have degenerate carbon, oxygen, or helium core, and then common envelope, outflow of common envelope, and then double degenerate. It depends in the type of which white dwarf they will be. It will be then it has more and different kind of life. For example, it goes to supernova type A, or if it has carbon, oxygen, or carbon, oxygen plus helium, and you see they have more and different kinds of life, and their fate will be different. At last, it will be, for example, single dwarf, white dwarf, supernova type 1A, or supernova type 1A, or neutron star. Thank you for your attention, and see you next time. Bye.